Hi there. Um, we're going to break this down as usual into 4 or 5 little short modules. The first module is going to finish up the material that we didn't quite get to on Friday. So it'll be um, on continuous time Fourier transform. Before we begin, though, I want to point out that there will be some homework due on Monday. Um, that's related to this lecture. And here are the questions. You can download and print this out. It's part of the Lecture 17 PDF, which is on the website. And just download it, print it out. If you read it before you listen to the rest of these lectures, you should be able to answer these very quickly and very easily because they're just taken right out of the lectures. They're not meant to be hard. This should be an easy 5 points. So without any further ado, let's finish up the material on continuous time Fourier transforms. Okay, um, these notes are also available for download, and you can print them out and just follow along. I decided that might be a little bit better for this lecture. So here's where we're at. We've talked about the continuous time Fourier series. Mr. Fourier said that all periodic signals x of t can be written as an infinite sum of sines and cosines, or alternatively as an infinite sum of complex exponentials. Okay, but he didn't say what to do with aperiodic signals. So we have to take a little bit of development to get to the case for aperiodic signals. What we're going to wind up with is the continuous time Fourier transform. So we'll use these abbreviations a lot, CTFT, CTFS. All periodic signals have Fourier series. Aperiodic signals have Fourier transforms. We'll find that this works as well for discrete time. Well, here's the story. We spend a lot of time on periodic signals. Here's a periodic rectangular pulse wave. All right, repeats at t0 seconds, has a pulse width of tau seconds. And when we do the Fourier series and write out the magnitude spectrum, we see that it's a line spectrum. All periodic signals have a line spectrum. Okay, that is something you gotta know. Periodic signals have a line spectrum. These lines are separated by the fundamental harmonic f0, which is just 1 over t0, 1 over the period. All right, and furthermore, the bandwidth of this thing, we can look at the bandwidth of this signal. Most of the energy is carried in this first lobe of the sinc function. That lobe is delineated by 1 over tau. The frequency of that first null there is 1 over tau, where tau's the width of that pulse. So real short, thin pulses, tau is small, means high bandwidth. All right. Well, what happens when t0, the period, gets really big? So we have to wait a long time for this second pulse to come in. In fact, if we take the limit and t0 goes to infinity, I have to wait an infinite amount of time for this pulse to come in. If that's the case, we say this is an aperiodic signal. It's not periodic. Instead of a train of pulses, there's a single pulse. Still the same pulse width. Okay, now if we think about it a little bit, it's pretty clear that delta F here, which is 1 over T naught, is going to go to 0. You know, as T naught goes to infinity, delta F is going to go to 0. So these lines become really close together, and there's a whole bunch of them. You know, there's just going to be a ton of these lines. I can't draw straight lines, but there's just going to be a lot of these lines, and pretty soon they get so close together there's a continuum of them, and in the limit we're just going to get a continuous spectrum. So aperiodic signals have continuous spectra. All right, you've got to know that aperiodic signals have continuous spectra. If you see continuous spectra without lines, you know it's aperiodic. If you see a spectrum that has lines, you know it's periodic. You've got to know that. Now, look at here. The pulse width hasn't changed. The bandwidth hasn't changed. 1 over tau is still 1 over tau. Notice that this is a power signal, and this is an energy signal. All right, we'll find out that this has a power spectrum, and this has an energy density spectrum. So there's a lot to be learned just by looking at a simple little graph like that. In the limit, the Fourier series converges to an integral instead of a sum. Let's see, I'm looking here. I'm looking here at the synthesis equation. This is the synthesis equation. It used to be a sum for the Fourier series, the sum of all the Fourier coefficients, but now it's an integral, okay? Because the df's are now infinitely close together, and we have an integral. So there's the inverse transform and the Fourier transform, also known as the analysis transform. Okay, notice that now we don't have kf0. This is the kth harmonic. Frequencies were listed in terms of discrete frequencies in the Fourier series. Now it's a continuous frequency variable f. Okay, so that's the big change. What about convergence? Well, the same properties. As long as the Dirichlet conditions hold, the continuous time Fourier transform is just like the continuous Fourier series. It does converge. And for all real-world signals, this is going to happen. So we don't have to worry about that too much. Gibbs phenomenon. Do we still have Gibbs phenomenon? And yes, we do. Same as for the Fourier series. Expect that overshoot will happen at discontinuities. Unless we have a system that has infinite bandwidth, there'll still be overshoot, but if you have infinite bandwidth, there'll be zero power in that overshoot, as we discussed in class. But in real-world systems, expect there to be these Gibbs years things. So if you have a discontinuity and you represent it as a Fourier transform and do this synthesis kind of thing, you're going to have the actual reconstructed signals are going to have these little overshoots at the discontinuities. All right, Parseval's relation. Parseval says that if you add up all the energy in the signal, x of t is the signal, square it is the power, integrated over time, power times time is energy. So this is the total energy in the signal in joules. Okay, Parseval says that joules in the time domain have to be the same as joules in the frequency domain. After all, this transform is entirely reversible. So if you have x of t, you can get x of f. If you have x of f, you can get x of t. And I'm not going to speak out the j2 pi f. That's just the book's notation. So don't worry about that notation. We could just as easily write x of f. But anyway, my point is the information in x of f and in x of t is identical. So Parseval reasoned that the amount of energy in one domain ought to equal the amount of energy in the other domain. And that's what's called Parseval's relation. All right, the important thing about this is it tells us how to interpret the spectrum of the signal. And look at this. I mean, it's real simple. If you think about the magnitude of x, quantity squared, that's times df. Well, df, we'll just do unit analysis here. df is in hertz, right? So if this whole thing is going to be joules, then this quantity, the magnitude squared, has to be joules per hertz. So we say that the magnitude of x of f, quantity squared, is called the energy density. Whenever you have a density, in this case it's energy per unit something. When it's mass density, it's kilograms per cubic meter, something like that. It's just a quantity that's been normalized to some value. And in this case, it's joules per hertz. So we call it an energy density spectrum. All right, moving on. Let's just do one example of the Fourier transform. We did some Fourier transforms back in 2220 as well. So this should be kind of a review. In fact, we did this exact same Fourier transform back in 2220. So what is the Fourier transform of a single rectangular pulse? Its pulse width is tau over 2. I'm just going to say it has a 1 volt for its height. And the way I set it up is that a lot of communication systems use rectangular pulses to send information. Like we could send a 1 or a 0, depending on whether the pulse was a 1 volt or 0 volt. That's a very common thing. So, for example, tau, the pulse width, could be 10 to the minus 6 seconds. All right. Well, here's the Fourier transform. We just plug it in. There's x of t. Just plug it in. We integrate over the non-zero range, minus tau over 2 to tau over 2. And they multiply that by e to the minus j2 pi ft. Okay, we don't have, in Fourier series, it was kf naught there, but now it's the continuous time variable, continuous frequency variable f. Well, this is one of the easiest integrals to do. This is just right out of the tables, evaluated from minus tau over 2 to tau over 2. Plugging those values in, we get this thing. Recognize that this is an Euler identity. Remember, e to the x minus e to the minus x is 2j sine x. Okay, so that's makes that easy to simplify. The two j's cancel, and we get pi f in the denominator and sine pi f tau in the numerator. So a real simple one to do. And then what we really like to do is get this into the form of a sinc function. Remember that a sinc function is sinc x is defined as sine pi x over pi x. Okay, so if we can get it into the form of a sinc function, we will learn a lot about the shape of this thing that we're going to get. And to get this into the form of a sinc function, you can see I need to have the argument of the sine be the same as the denominator. And if I multiply by tau over tau, I get there. You see, now I've got pi f tau as the sine argument. I've got pi f tau as the denominator, and that tau sort of floats out there in the front. So we wind up with tau sinc f tau. So this is the Fourier transform. This is totally real, so I can plot it as an amplitude spectrum. Remember, if it is real, you can just plot it with one plot. If it's complex, you need a magnitude and phase plot. Well, here's the sinc function. Remember, it has unit height at the origin. Unit height times tau means its total height is tau. And it has zero crossings whenever the argument is equal to 1. So whenever f is equal to 1 over tau, we're going to have a zero crossing. So the first zero crossing is 1 over tau. So there's the amplitude spectrum of a single rectangular pulse. It's just a sinc function. Now in my little example, I have 1 microsecond rectangular pulses in this communication system. So the approximate bandwidth, which is this shaded area, we don't generally count negative frequencies when we compute bandwidth, but we go out to 1 over tau. That's 1 over 10 to the minus 6. That's 1 megahertz. So if you have 1 microsecond square pulses, your bandwidth is approximately 1 megahertz. If we want to draw the energy density spectrum, okay, we would plot the magnitude squared versus frequency. So this thing is in joules per hertz, and I've just basically squared this thing. The peak value of tau here is now tau squared. And you can see all the negative quantities are now positive. And so that's the energy density spectrum. And finally, I have a little note. We can answer questions now. Finally, how much energy is contained within the approximate bandwidth? So if I asked you how much energy is in any bandwidth, you just have to integrate the energy density spectrum over that range. And in this case, I said, how much energy is contained in the approximate bandwidth? We have to tally up both the positive and negative frequencies. They both come together to build up this rectangular pulse. So I have to integrate from minus 1 over tau to plus 1 over tau. That's minus 1 over tau there to plus 1 over tau of tau squared, sinc squared, df. And that gives us the total joules. Now that's a hard integral to carry out, so I'm not going to take that any further, but I just wanted to point out that we can now calculate how much energy lies in any given frequency range. All right, so that's the end of this module. Went a little long. We're going to pick up again and start talking about discrete type signals and their spectra.